comments fairly generic. There will be times where I note particular components of this process or textures of this process that are specific to the modeling methodologies. As in this, as in most of the other presentations, I can only touch on bare essentials of some of the items. You'll find, again, quite a lot more depth of coverage on the online material that's available to you in the form of videos, in the form of slides, in the form of example models illustrating many of these components. So I can be talking about modeling process here, and it's worth reflecting a little bit on the context of dynamic modeling. Typically, this is an ongoing process of refinement. I touched on that point earlier, and I'll get to it again. And as I indicated this morning, the best thing to do is in the ideal world, one can iterate this with further data collection that's informed by model understanding of key uncertainties, and by observations of interventions that are undertaken, perhaps informed by the model, to cross-check model anticipation of possible outcomes. I noted this morning that there's a lot of emphasis in the modeling process yielding insight. It's been noted that sometimes the modeling process is one that brings together groups that are often at loggerheads otherwise, that helps them recognize, done right, helps them recognize the fact that they are linked in a complex system, and where, while to a first order naive approximation, they might think that they're competing for resources with another group, often it's discovered that because of the close coupling, if that other group isn't well resourced, you end up bearing the consequences as well. We've run modeling studies in my consulting career, and I've seen it in academic study as well, where two groups that were formerly at loggerheads realize they depend on one another in so many ways that it's very important that the other group is well resourced, it is well supported, and they'll combine efforts to secure appropriate levels of support. I noted this morning that, just in passing, the great importance that I place on incremental model development. This is not something you will find widely discussed in the literature. It partly is a reflection of the fact that I teach software engineering, and incremental development methodologies are front and center best practices within software development for many similar reasons you see them in modeling. You will put your project at risk, and you will fail to realize its full potential unless you apply an incremental methodology for building it up. It's that important to work step by step. And it's important for two different reasons. One is the question about whether we've built the right model, and the second is the question of whether we've built the model right. In short, incremental development can help us secure insight faster for models and more adaptively shape our modeling efforts based on the learning we've secured through early model experimentation. The other component, so that's getting the right model, making sure that we're building a model that speaks to our real needs and that secures us the sorts of insights that we're seeking to gain. The second reason, though, is about building the model right. Just because we aspire to build a model that captures certain features of the external system, that captures certain phenomena, that doesn't necessarily mean we'll do it correctly. And one of the challenges you'll find, particularly in more complex models, not unique to agent-based modeling, but the problem is particularly pronounced there, is the fact that as we build a more complex model with more moving parts, there's more things that can go wrong. And with incremental development, the best practice is for each successive version of a model you build, even if it's not your final version, even if it's not one you hope to show to a stakeholder, you so-called dock it against the earlier version, and you observe the differences. You add a small piece in. Maybe it's a single transition. Maybe you add in waning of immunity, for example, after that was omitted. Maybe you add in a state for cavitary TB when there wasn't that state earlier to capture severity of infection. When you add in something like that, you run the new model, and you compare it to the behavior of the previous one. And best practice is you compare the behavior with that new feature disabled, just make sure they yield the same results, which they should. Then you enable that new feature, and you observe the difference in behavior. And if there's an insight to be had, a new dynamic caused by that feature, caused by, say, waning of immunity, or the occurrence of the representation of severity of disease, you will get that insight right then. You'll be able to know where it came from. Okay? If, on the other hand, there's a bug in your model, if there's a defect, you didn't realize it, you thought you were putting in the average time with illness, and instead you put in the chance per unit time of recovering, you will discover that problem sooner by comparing each little version with the previous version. And in some cases, these incremental versions can be demonstrated to system stakeholders and inform insight as to what to do next. And there's a variety of reasons we do this sort of model development. So while I'll be talking about the modeling process and its stages, you should realize that those are done in an incremental fashion. And you will secure great benefit by building up incrementally. One of the particular dangers, I have to say, with agent-based modeling, and I speak from someone who uses multiple modeling types, is that there's tremendous flexibility associated with the method. We can essentially posit all sorts of complexity in the underlying system and describe it quite adequately with an agent-based model. The problem is that often we end up with a model with everything in the kitchen sink thrown in, and we run it, and we see some behavior. We don't know where it's coming from. We don't know what gave rise to this behavior, what particular features caused this oscillation to occur, or led to this unusual behavior or this great sensitivity. If we build it up incrementally, we see each of those features coming into play, and we understand the distinctive contribution of those features. So it's really important for model insight that you build incrementally, and it's really important for model correctness that you build step by step. The work I'll be talking about today is also contextualized by a couple of modeling processes that have been advanced for different sub-disciplines within modeling. Within the system dynamics area in particular, there's been a lot of thinking and a lot of very conscious attention played to the modeling process, comparatively more so than for, say, agent-based modeling, although in recent years that's been advancing. So, for example, you'll find certain modelers like Khaled Saeed. He has a very detailed 12-step process for system dynamics modeling. Within agent-based modeling, there's two prominent frameworks. One is known as the PARTE framework, standing for Properties, Actions, Rules, Time, and Environment. And there's another framework known as the ODD framework, so Overview, Design, and Details of Methods. There's some very good expositions of this. I would strongly recommend for anyone who's interested in agent-based modeling that you check out the quite new book by Railsbeck and Grimm on individual-based and agent-based modeling, which is really a very worthy work, and many components of it bear careful attention. I'm not going to have a chance to go into those. If you go to my online lectures, my agent-based modeling class, the one at MIT, the one at U of S this past semester, I go into those frameworks in detail, particularly the ODD framework, and that may be worth checking out for those of you interested in it. But I want to talk about this modeling process in its various stages, because otherwise, when we show different components, you won't have an understanding of how they fit together. For example, when we talk about calibration, we talk about sensitivity analysis, or indeed, if we show qualitative models, you won't quite understand how they articulate with one another into the overall whole. The modeling process, broadly speaking, and you know, one can quibble with the breakdowns here, but it proceeds in a set of stages. And if you're doing incremental modeling, often you will do elements of this for each increment, successive increment of the model. So in the first stage, we'll conceptualize a model, and very critically, we decide on model scoping. What's the boundary of the model? So within this early stage, we're often focused on the problem we're seeking to explain, or the research questions we're seeking to understand. And we want to crisply articulate those so that we can craft our model. We use them, as John Sturman comments in the system dynamics area, as a logical knife to cut away unnecessary complexity. One of the biggest mistakes students in software engineering get in when they learn object-oriented programming is they say, wow, we can have an object for a person, and we can start adding in all sorts of detail on a person. And sky's the limit. The mechanism, the modeling methodology doesn't really restrict you much. And so you can put all sorts of things in. But that is an opportunity cost. You can't use the time you're using to incorporate those things to secure insight from running the model. You can't use it to refine the things that really matter. So it's best to marshal your efforts. Focus them on the things you think matter the most. Learn from the early experimentation model and add things in as you think of them as necessary in this incremental way. So try to identify model scope. And using our statement of a problem is very, very important. What are we trying to do? Are we trying to explain some reference modes, some behavior over time? Are we trying to explain a set of patterns that evolve behavior over time and spatial patterns, for example? Are we trying to understand some trend that we've observed, for example? Or are we trying to understand policy impact among a couple different policies? Are we trying to simply just rule out a few hypotheses or see if certain simple mechanisms could provide very simple explanations for otherwise complex patterns? These are different purposes, and you'll find that models out there differ hugely in the purposes to which they aspire. Some are very, very grounded in empirical data, seek to kind of characterize the relevant aspects of the world germane to the issues at hand at a quantitative level so you can do quantitative policy trade-offs. Others seek to communicate broad insights. For example, the Schelling segregation model shows how segregation can emerge within communities. Situations originated by an American sociologist showing how in American cities, blacks and whites can end up living in very segregated neighborhoods, even with only slight preferences between them. It's not seeking to depict Chicago. It's not seeking to depict Washington, D.C., or seeking to depict New York City. It doesn't aspire to that. What it's trying to do is communicate an insight that slight differences in preferences compounded among many individuals and coupled with mobility can yield big disparities. And that's an insight that is the purpose of the model. So with model purpose, typically we're using it to strip away unnecessary complexity, and we end up starting with only the things we think are absolutely most important and incrementally adding things in as we learn. There's a principle in software development called YAGNI. You ain't gonna need it. So the principle is you start with things just those things you're absolutely convinced have to be brought to the table, and you don't speculatively add things in unnecessarily. The common division here, and this is well articulated in the system dynamics literature, is amongst three sorts of things. And this applies to all the modeling methodologies. There are some components that are going to be endogenous in your model. Your model is going to provide a generative explanation for them. It is going to try to reproduce them using dynamics. They will be calculated by the model. I'm using different words for it. The point is that the model, much of the model dynamics is going to be spent in producing dynamics associated with these factors. Another set of factors will be exogenous. They'll be represented, but they'll be represented in a fixed fashion or a fashion that changes in some predefined way. For example, you may have a representation of interest rates in your model, but you'll assume that those are specified by some time series. It's not calculated by the model, it is specified to the model. Or maybe it's immigration rate or the total, the size of, the birth rate going forward based on projections. So these are specified to the model. It uses them in its internal workings, but it doesn't seek to calculate them and to drive them. The final set of things are ignored or excluded. These are things that lie outside the boundary of the model. And what I'd like to propose, folks, is that you consciously decide and sort different things you could put into the model into each of these three categories. The fact that you've consciously reflected in that fashion will help ensure that you haven't just unconsciously overlooked something or unconsciously put something in that you don't really need to be in there up front as an endogenous factor. So try to sort your different components of relevance into these factors, and it's no shame that you ignore it at first. You consciously say, we're going to put this aside, learn what we can from these other factors, and later we'll go back and we'll re-examine this. Each incremental version of the model may reshuffle things a little bit. Some things that are ignored get put in exogenously. Some things exogenously we try to explain. There's a very important concept in agent-based modeling called pattern-oriented modeling. And this particularly originated with work by Volker Grimm in ecological modeling. And it's well described by a Science article from 2005, I think it is. And it's also described in their book, the book I referenced earlier that he wrote with Railsback. The observation here is that agent-based models are extremely flexible, and frequently it's not enough to simply articulate a model purpose ahead of time and expect that to fully dictate our model scope, what's in our model, what's excluded. Instead, we want some more guidance. And what we turn to in agent-based modeling, and quite similar phenomenon goes on in system dynamics modeling, is patterns of sorts. In system dynamics, these are called reference modes because we're reasoning about patterns of the system behavior over time. In agent-based modeling, we typically have recourse to a larger set of patterns because we may be dealing, for example, with patterns over space, or patterns over networks, patterns over longitudinal behavior of individuals, not just cross-sectional behavior of the population, as you'll see in an aggregate model. And in these cases, we will seek to leverage these patterns as things that we're seeking to explain in our model. So the purpose of the model here will be partly to explain these patterns or to stay true to these patterns. So patterns are pieces of information which, if our model didn't match them, would cast suspicion on the reliability of the model. They're typically specific to a purpose. And the insight here is a particular pattern may be quite modest in its specificity. For example, gonorrhea. We know that gonorrhea rates for many countries for women are actually significantly higher in terms of prevalence of infection than for men. And it has to do with asymptomatic infection, etc. And we'd like our model to reproduce, say, that pattern. You might say that's a very weak pattern, and that's true. But once you start combining it with other patterns, it may be that it gets more and more specific and rules out more and more models. So we will often turn to patterns like this. This is patterns, you've seen some of these earlier in my slides, patterns of, say, cycles over time. Phenomenologically, we want our model to reproduce multi-year cycles associated with traditional childhood infectious diseases. Maybe it's a rebound pattern like this. We have work published on chlamydia rebound patterns, which examines that. Maybe it's longitudinal data at the individual level. We want to capture individuals' characteristics, sort of time frames of recovery from infection, etc. We want to be able to characterize their trajectories over time. The fact that perhaps certain frequent flyers in the sexually transmitted infection front tend to come in with infections many times during a year and explain a very large fraction of all infections. We might like to characterize individual level longitudinal patterns of their history or biography, as Jeff calls it, which require or merit explanation. And this data is notable because it can be very hard to explain with an aggregate model. Capturing trajectories of individuals is something that in aggregate modeling is an exercise in frustration often. We may want to capture aspects of emergent network structure. This is case contact data from Saskatchewan we work with TB. And we may want to reproduce these patterns in our TB contact tracing model because this is the result of a contact tracing process in the external world. We may want to match degree distributions. How many, so if you look at a person, you use a histogram to approximate the empirical distribution of how many people, how many contacts they're associated with. We want it to match this data. Or we may want to match infection spread data like this. Spatial data. We saw this earlier in terms of variability of heterogeneity. We also observe in some of our models scaling relationships that merit explanation. In terms of why do we see this data in the external world that involves such a nice scaling relationship between behavior A and outcome B. Empirical distributions associated with observations of individuals, say here, according to how many contacts they have, what's their likelihood of being infected. Or here, just overall aggregate data over time for different years showing changes in TB prevalence in one community in Manitoba involving sort of cycling of that community. In many cases, our patterns will be multiple levels in scale for an agent-based model. For example, we may have some data on individual level factors, some data involving contacts between individuals and places shown up there, with places being triangles, individuals being squares. May have contact data on individual networks, and then data on number of cases over time showing this waxing and waning pattern. And we'd like our model of TB in that community to simultaneously reproduce these so-called patterns at each of these different stages or levels of the model. In some cases, what we're seeking to reproduce is more the phenomenology than actual data. We want to see waves over time in our model, and we're not so interested in point matching of historic data. Particularly in stochastic models, point matching is sometimes not going to be the priority. Our model would be producing patterns that are characterized, say, by successive waves of infection over time, but the exact timing of a given wave will vary according to the vagaries of who happened to contact who at what time, etc. And they're trying to do point matches against historic data is often a fool's errand. Fool's errand because the observations in the external world are fundamentally observations on one realization of a very complex process that involves stochastics. And instead, what we want to do is match statistical properties associated with our model. So in this early process phase, problem conceptualization, we're trying to decide on what is the goal of our model and what is the scope of our model. Endogenous, exogenous, and excluded are some of the most important distinctions. In a later stage, and this is common to agent-based modeling and discrete event modeling and system dynamics, but it's mostly talked about in the system dynamics literature, we do what's called problem mapping. And in system dynamics, this is a very well-emphasized process because it often involves a stakeholder and help confer insight early on. So we will have a model mapped out, perhaps in terms of stocks and flows and in terms of feedback loops over time, and we'll use it to kind of gain some sort of high-level understanding of the relationship between various factors. Within an agent-based model, though, we'll see qualitative artifacts used as well. Some might be a flowchart. This is from our TB contact tracing work, showing how does contact tracing work within our province. You go in for a skin test, you get a first skin test. If it's positive, then you're summoned for clinical review. Otherwise, you go on to a second one. This will capture some elements. This expresses some things we're hoping to capture in our model. We may use state diagrams as qualitative descriptions of what our dynamics we want to capture. Later, we'll go in and associate transition probabilities, perhaps time-varying transition probabilities that vary with an individual's age or history. We may go in and associate those with these transitions. But up front, we use it as a qualitative depiction, a map, as it were, of the characteristics we're hoping to use to describe an individual's behavior over time, their dynamics associated at the individual level. We may have a state diagram this for TB, or here interaction between multiple comorbidities, tuberculosis, diabetes, and tobacco use, which is a confluence of syndemics, particularly in our Aboriginal communities that we're seeking to address. There's a variety of mechanisms from computer science, this being called a UML, a Unified Modeling Language Diagram, which we'll also sometimes use to good effect within model mapping, sort of diagramming for different types of agents or different types of components within our model, what features we expect them to support. For example, for a person, we'll keep track of for example, whether they're a newborn, whether their sex, their age group, some count of times they've previously been traced, whether they currently have infectious TB, etc. One of the most powerful mechanisms, though, and one that's strongly enabled by any logic, is the use of state transition diagrams that are richer. And this shows some hierarchical diagrams. This is from a model you'll be seeing later, which involves agent mobility. And here we're capturing behavior over many seasons. This is for deer movement. Over many seasons, the differential behavior associated with deer, for example, their rutting behavior, the behavior during the mating season, and its interaction with other physiological necessities such as finding food and water. And AnyLogic's support for rich state charts provides very powerful mechanisms of compactly describing certain common attributes. The gentleman back there asked, for example, about attributes that would involve common transitions from each of these states, and through the use of hierarchical state charts, you can capture in economy and with expressiveness some of those common linkages. So model mapping is about describing what we're hoping to capture in the dynamics of our model, the overall dynamics at a high level. The next stage is model formulation, where we're actually diving down and we're trying to fill in all the details requisite to make this model something that can be run, something that can be run to yield quantitative output. And typically this involves specifying things like state chart transition, formulas for flows in terms of stocks or intermediate variables called auxiliary variables, specifying processes, observer processes, statistics on the population, such as AnyLogic supports very readily, so that over time you may calculate the number of people in with different characteristics within the population. Or it may involve calculated flow statistics, how many have gotten infected in the last unit of time. And typically we'll fill in parameter values, particular quantitative estimates that adapt our model to a particular context. So at the model formulation stage, we're seeking very much to arrive at a fully quantified model, and a model that will be suitable for securing quantitative insight. Within this stage, there's often going to be a premium on observing model behavior and making sure that you haven't missed any very, very important components of the model formulation. So each of the approaches differs in the level of detail they provide. Stock and flow models, you're using a small number of components in very creative ways. You build up aging chains, or you have co-flows, or you have really rich combinations of these stocks and flows to capture certain phenomena that aren't captured at an individual flow level. Within agent-based modeling, we have a much larger modeling vocabulary that needs to be marshaled, and some of the components of it are described here. Within the agent-based modeling literature, particularly, there's a set of desiderata that are, excuse me, they're not desiderata, they're more considerations that you want to be consciously thinking about when you're at this stage or even earlier stages. For example, to what degree do you want your agents to adapt to the environment around them? Are they sensing information about their local environment and using it to make their decisions? how is that going on? To what degree is there learning involved? To what degree do they change their behavior over time based on their experiences, say adverse experiences when presenting for care at a clinic? To what degree might that lessen their likelihood to return to that clinic or even to present for care in the future? So how might it modify care-seeking behavior or risk perception? How might it modify an individual's risk behavior? You'll be wanting to think about stochastics and interactions between individuals. Again, my online materials, I go into each of these topics in greater detail in a way I don't have time to go to here. Model parameters within these models are commonly drawn from a variety of sources. And it's not infrequent that we use statistical methods. In fact, it's very common we'll use statistical methods to arrive at appropriate parameter values. In other cases, we draw parameter values based on secondary literature, based on controlled trials that have been undertaken, in some cases based on expert judgment of individuals. And we'll often introduce those into parameters in something like AnyLogic, and they'll make their way to being associated with the throttling of these transitions. The model calibration phase is a quite textured one. And as for each of these, I only have time to go into bare essentials, although they'll be particularly bare here. We will be talking more about model calibration later in the week. But the overall insight here is that often we don't have reliable information on some model parameters. We may be positing behavior within the model that is difficult to observe, at least with traditional instruments, or perhaps at all. And these parameters associated with that behavior may be hard to, therefore, estimate. And frequently what we will do with models like that, we will attempt to take advantage of the fact that the model exhibits emergent behavior that can be compared with data. So we may have data about broad behavior of pieces of the model or pieces of the system or the system as a whole, which we can compare to model behavior. And so although we may not have behavior, any one piece of data that can inform a selection of a model parameter value, we want to select a parameter value that will yield overall model behavior for sub-pieces of model that stays true to observed data. So we engage in this process called calibration, and conceptually involves this sort of triangulation. You use the pieces of data you have to figure out what the values of those parameters that are ill-known, what those values must be to be consistent, to yield model behavior consistent with the observed behavior. So here we're using emergent behavior to match historic understanding. And sometimes, often we learn from this that our model structure just can't produce those patterns. And that's, ladies and gentlemen, what keeps us honest in many cases. It forces us to go back to the table and say, you know, we need to separate the uninfectious TB state from the infectious TB state, for example. We've been sort of glomming them together. I don't feel that comfortable about that, and maybe that's why we can't match this data, because really we're securing very different levels of likelihood of discovering someone at each of those stages. So you go back and you refine the model some to better match this data. In best practice, what you should be doing, however, is trying to match a bunch of the data you have in keeping some other data put to the side. And then when the model is fully calibrated at an adequate level to the data you're trying to match to, you compare its predictions for the things you haven't told it about in the calibration process. You compare its predictions to what you've put aside. And that will, if it predicts these things that were not in any way presupposed by the model, were not used in model calibration, and yet it predicts them, that helps build confidence in the model's reliability. So this calibration process is often quite involved and involves a lot of learning. And AnyLogic as a platform is I think quite distinctive out there for agent-based platforms in the support it provides for calibration. Calibration for agent-based models is particularly tricky because it involves stochastics as well. There's variability in the model results for a given set of parameter values. And AnyLogic has tools in the form of Monte Carlo ensembles that can be run during calibration to really allow for dealing with those sort of challenges. In this case, we're seeking a single model to match many, many outcomes. So this, for example, is data from diabetes and diabetic ESRD in Saskatchewan, and we're seeking the model to match simultaneously all these time series. This is a system dynamics model, hence the underlying curves from the model, the sort of red and gray here, are very gradual or quite smooth. In an agent-based model, we'd be capturing the stochastics as well. We'd be capturing the variability, and that might be something we try to match up, the degree of variability in model results compared to historical observation. So here we're operating a parameter space. We're adjusting parameter values, say how long it takes you to that you stay in an asymptomatic state, or your likelihood of transmitting to someone given a discordant contact, a contact between an infective and a susceptible, the likelihood of transmission when using condoms or something like that. You might calibrate that value, and that might be one of the axes here, and you're calibrating often many things at once. Here we're often doing calibration against model results that are quite variable for small numbers, situations where we have small numbers. I have to finish up here, so I'll just make some very brief remarks about these final phases. Model testing is a very, very rich topic. There's a variety of tests we use against our model. Some of those tests are tests against data that we haven't told the model about in calibration. We try to match it to this data to judge the degree of its predictive value. In other cases, the tests that we conduct are tests associated with correctness. For example, are our model units consistent? Or are we doing something similar, like adding a count of people to a number of dollars? Something which is numerically possible to do. 1 person plus $2 is 3, but it is meaningless semantically. And the risk there is that we will have a model which is doing meaningless things. And tools like AnyLogic and some system dynamics packages provide support for unit analysis. And there's a rich set of approaches you can use, from dimensionality analysis. And there's a set of techniques involving uncertainty analysis in the form of sensitivity analysis of a model, examining the degree to which model results are contingent on particular values you've estimated for parameters, how much they vary with changing parameter values. And you may do extreme value tests, case where you observe model observe model outputs when you adjust parameter values over wide ranges. There's a set of robustness analysis to try to recognize cases where a model may be robust or may have shortcomings. It may be very contingent on the particulars of the data that we have available, overfit, as it were. In the policy evaluation phase, we'll often associate our model with interfaces that can be used by non-technical policymakers, or at least those other than the modelers themselves within the research team. So, for example, this is an interface created by one of my master's students for a TB model, which allows you to examine different scenarios that could be run and examine outcomes in terms of burden of infection, in this case prevalence of TB infection, predominantly latent infection, over time for different scenarios. So we're running the model, typically for a given scenario, for a given sort of intervention. We'll run it many times for an agent-based model because it's stochastic, and so we'll have to run a Monte Carlo ensemble of, say, 30 runs in this case. Sometimes it can be hundreds of runs. For a system dynamics model, we will have less, you can have stochastics commonly, however, they're deterministic, and you only need to run it once for that scenario. In a discrete event model, we may run a set of an ensemble as well because of stochastics associated with the vagaries of procedure times or what have you. We'll observe variability in results often and reason about statistical significance of one intervention's results from another, etc. In the knowledge translation phase, we'll also seek to work with broader sets of stakeholders, using the model sometimes as a tool for communicating high-level understanding. And this is something Jeff has done some wonderful work in just trying to learn from very sophisticated agent-based models and to really boil it down to very, very simple, say, stock and flow models, which can then be presented to stakeholders to help improve insights, help improve intuition on their part for how the system works, something that I think has enormous benefits that it can confer. So a few key take-home messages from this abbreviated lecture. So models express dynamic hypotheses about processes, and models are specific to purpose. We are seeking to understand how diverse pieces of a system work together, and we do that in a quite detailed step-by-step process, which is best undertaken in an incremental fashion. It's best undertaken in a step-by-step fashion where you add pieces in as you believe they are necessary, and you learn from each successive experiment rather than throwing it all together in a big bang sort of way. This process is articulated. There's cross-checks we do at several components of this process, and for a given model, some things may be played down. For example, if we're developing a model for insight, predominantly for high-level aha possibility, and we're not so interested in characterizing an actual observed historic context, we may really play down the model calibration side. Those sort of models may sound mysterious, but they can really give a lot of useful intuitions to people in prioritizing their day-to-day activities without requiring a lot of data, without requiring a heavy investment up front in securing data. So these stages they will vary in terms of how much emphasis we put on each for a given model, but they do occur in a sort of continuum. And one of the things you'll see within this this lecture is models at different stages of development here and with different goals associated with them. So I've overspent my time here. I think it's time for lunch, if I'm not mistaken.
Yes, I want to ask Nathan a question.